Go anywhere in the modern world and I'm sure it won't be long before you hear this sound. It's the sound of air conditioning, and I'll bet most of you have never considered how important this invention is. Air conditioning is what allows us to massively extend the shelf life of the food we eat. It's what keeps our electrical devices from overheating. It's what has allowed us humans to settle comfortably in almost any region on Earth. But it's also one of the worst things for our global climate and energy usage. 10% of the energy produced in the US alone goes into air conditioning, 6% of which is completely from residential buildings, costing homeowners $29 billion a year and releasing 117 metric tons of carbon dioxide in the atmosphere per year. And on the worldwide scale, this number gets even worse. As developing countries continue to increase their infrastructure, according to the International Energy Agency, of the 35% of the world's population where the average daytime temperature is above 25 degrees Celsius, only 10% own an AC unit, meaning the amount of air conditioners can increase by 2/3 by 2030. What if there was a way to fix this? What if there was a completely energy-free alternative for cooling our spaces? One promising way to do this is through a process known as passive radiative cooling. The coolest thing about this approach is that it can be done in such a way that heat is literally beamed into outer space. In general, there are 3 ways to transfer heat. The first is conduction, where heat is transferred through physical contact and the vibration of one molecule spreading to the next. This is probably the most familiar form of heat transfer. For example, when heat from the base of a hot pan travels to its handle. The second is convection. This is the process by which heat is carried away by fluids. For example, a fan blowing air onto you to cool you down on a hot day. The third way is radiation, and it may be less familiar than the others. Through radiation, heat is transferred through electromagnetic waves. It requires no medium to work, and is the way in which sunlight reaches us through the vacuum of space. For our purposes, this last one is the one we are interested in. Now that we have a basic understanding of what radiation is, here's a simplified equation describing which factors go into optimizing it. Now stick here with me for a moment. I promise this is going somewhere. Here Q is the rate which heat energy is transferred from our cooler in watts per meter squared. There's a few other terms like the heat transfer coefficient H and the surface area A, but let's gloss over those for now and consider the last term. This represents the difference in temperature between the cooler T and the environment it's radiating into, denoted by T infinity. Simply put, the greater this difference, the more cooling power radiation provides. All of us might know this intuitively to some degree. If you want to cool down something hot fast, we want to put it in contact with something as cold as possible by comparison. Now, what's a place we could dump heat into from anywhere on the surface of Earth that's really cold? Space. Outer space is really, really cold. At 2.7 degrees Kelvin, or minus 455 degrees Fahrenheit, it's colder than liquid nitrogen. But how could we even send our heat out there? Wouldn't any heat we try to send up simply be absorbed into the atmosphere? As it turns out, if you can radiate heat out at a wavelength between 8 and 13 microns, known as the atmospheric transparency window, it will pass straight through the atmosphere without interaction. This is the challenge scientists have been trying to crack since the 1960s. So if passive radiative cooling is so good, why isn't it everywhere? Why aren't we getting rid of our outdated air conditioners and replacing them with this seemingly limitless cheat code of free cooling? The short answer is that this technology is still in its infancy. It still needs time for researchers to bring up its thermal efficiency and lower its costs. Right now, even the best radiators we have only reach a heat flux of 105 watts per meter squared. To put that in perspective, if we took an average household air conditioner at the moment, we find that they run around 48,000 BTUs, or around 14,000 watts of cooling power. In order to get the same amount of cooling power with passive radiative cooling, we would need a passive radiative cooler with an area of about 133 meters squared, or half the area of a full tennis court. For those of us who don't live in mansions, imagine trying to put that on top of your roof. This huge size is also bad because at the moment passive radiative coolers are really expensive and difficult to mass produce. A lot of complex materials engineering is put into current-day passive radiative coolers. A very specific arrangement of materials with unique optical properties must be created in order for them to function. They must emit radiation in just the right wavelength range to fall within the atmospheric transparency window. Yet they must also simultaneously maintain high solar reflectivity so as to not also absorb heat from the sun. These are all daunting obstacles for the technology, but there are some possible solutions in the working right now. For example, scientists are trying to use a method of electrospun polymers, in which electrostatic machines squeeze polymers into any desired shape to create radiative coolers. If they are successful, this could lower costs and provide engineers with greater control over the optical properties of the material, which would help them improve performance. There are also some early signs of commercial success in the market right now. For example, 3M currently has a line of film coatings using radiative cooling technology, which it advertises for use in cooling roofs, data centers, and buses. In 2021, a company called SkyCool Systems received $3.5 million in funding from the Department of Energy to research passive radiative cooling systems. The company claims it has already tested its technology on a grocery outlet in Stockton, California, saving the store $5,800 in cooling costs a year. So to recap, passive radiative coolers have incredible theoretical potential. As global temperatures rise and worldwide infrastructure improves, there will be a growing need for lower energy solutions for air conditioning buildings. Passive radiative cooling seems to solve this as it needs no energy to cool buildings. By sending heat to space, which is very cold, they also have great theoretical cooling ability. Yet they are lacking in cooling efficiency, and they are very expensive to manufacture at the moment. In order to see passive radiative cooling put a real dent into the market and become the new king of air conditioning, it needs more funding and development. Researchers will have to come up with new materials which are more efficient and cheaper to manufacture. The fact that organizations like the US Department of Energy are investing in this technology is a good sign of early progress. However, there just isn't enough real-world data on its success so far to say for sure where the technology may end up. That might sound bad, but the same could be true for many other renewable energy technologies at some point. In 1954, researchers at Bell Labs announced that they had finally created a solar panel which was efficient enough to power a Ferris wheel. A toy one. One only around the size of a bicycle wheel, in fact. Fast forward to 2020, and solar energy made up 3% of energy production in the US. Passive radiative cooling may very well take the same path as solar panels did. It was only around 2014 where passive radiative coolers were efficient enough to work in the daytime without being overpowered by the heating of the sun. Whether or not passive radiative cooling actually sticks around, researching into it is still a worthy effort. Global warming may become a massive technological problem for us to overcome in the coming decades, and we need to evaluate as many technologies as possible to expand our toolbox for fighting climate change. Thank you all for watching.